Good afternoon, everyone. My name is Zhen Yichen. My presentation is about deep neural network accelerated detonation simulation. The presentation will be divided into the following 4 aspects. Combustion can be divided into 2 forms, deflagration and detonation. Detonation is regarded as constant volume combustion. The shock wave couples with the combustion wave, and the heat is conducted by shock wave compression. In detonative combustion, the heat release is rapid with low entropy increase, and the theoretical thermal efficiency is high. CJ theory is proposed by Champ and Jugert. It is a classical theory in the detonative combustion. When the velocity of downstream flow is solid relative to the shock wave, which also corresponds to the lost entropy increase, the parameters of the flow field are named as CJ state. The theoretical parameters of detonation wave can be determined by CJ theory, which agrees well with the experimental results. It is a common method to calculate the source term of a chemical reaction by solving ordinary differential equations. However, the solve of chemical ordinary differential equations constitutes over 18% of the total computation time in practical simulations. The computation cost is expensive. In order to improve calculation efficiency, deep neural network is a promising substitute for chemical source term calculation in combustion simulation, especially for the detonation problems. As an unsteady simulation, the time step is in the order of 1 times 10 to the minus 9 seconds, while the physical evolution time of flow field is about 1 times 10 to the minus 2 seconds. Therefore, number of the iteration steps is large and the computation time is unbearable. Moreover, detailed flow field cannot be captured by simplified chemical mechanism. As the figure shows, unstable structure named as S1 and S2 cannot be observed with the one-step reaction mechanism. However, computation cost of complicated chemical mechanism is expensive. Therefore, our work applied DNN in the detonation simulation to accelerate calculation. This picture presents the flowchart of calculation process. Flow field parameters such as temperature, density, and mass fraction of species are obtained by solving governing equations are set as input of the deep neural network. The deep neural network predicts chemical source terms and the time advance continues. These are the governing equations of mass, moment, energy, and species. The simulation is conducted in a one-dimensional detonation tube whose length is 1.5 meter. The left area of the computation domain is ignition region, and the premixed hydrogen and air with 1 atmospheric pressure and 300 Kelvin is pre-filled. The calculation is performed on an open source platform named DeepFlame, which is based on 3 other software, Cantera, OpenFOAM, and PyTorch. The convective flux is calculated by KMP scheme, and the time advance adopts the implicit Euler method with the time step of 1 times 10 to the minus 9 seconds. 9 species and 19 reactions chemical mechanism is used. Because the propagation characteristics of detonation wave during ignition are quite different from the stable stage, the DNN is only used to calculate detonation wave with stable propagation in our research. The flow field parameters in the stable propagation stage are set as initial field, and the DNN is used to predict chemical source terms. This figure shows the training flowchart of DNN. Before training, data generation, augmentation, and preprocessing need to be performed first. As for data generation, temperature, density, and mass fraction of species are obtained from 10 different cases, whose equivalence ratio ranges from 0.96 to 1.05. The data is sampled every 5 times turned to the -6 seconds when the detonation wave is in stable propagation stage. The data whose temperature is higher than 500 Kelvin is selected to avoid the sample from unreacted region, affecting the training of DNN. Then taken sample value as initial state. Time advance is adopted by Cantera with the time step of 1 times 10 to the -9 seconds. The training data consists of initial temperature, density, mass fraction of species, and the change of mass fraction. Random perturbation is applied for data augmentation. As for temperature, density, and nitrogen, linear perturbation is adopted, where for the species excluding nitrogen, an exponential randomization strategy is implemented. Heat release constraint is performed to eliminate non-physical training sample. The heat release rate of perturbed samples need to be within a certain range, which is set according to the heat release rate of the original data. Box cost transformation and z-score normalization are adopted for data pre-processing. BCT provides a more uniform distribution of small-scale clustered sample data, thereby enhancing the performance of neural network in predicting the species mass fractions changes. The input of DNN is temperature, density, and the mass fraction of species with BCT, and the output is change of species mass fraction. Multi-layer perceptron with 3 hidden layers are adopted. Gaussian error linear unit is used as the activation function, and the Adam algorithm is adopted for hyperparameter optimization. The loss function, including mass fraction unit conservation, energy conservation, and the physical constraint of heat release rate are presented here. The picture shows the influence of numbers of hidden layers. Taking into account both computational accuracy and training efficiency, 3 hidden layers is adopted. The upper figure illustrates the distribution of heat release rate and temperature along the detonation tube in one case. It can be known that after the detonation wave, the heat release rate drops dramatically and it decreases slowly with a high value. Then it drops rapidly again. The sample data of all cases can be divided into 2 parts. One is the data with a high heat release rate, and the other corresponds to low heat release rate, as the lower picture shows. This table lists the training sample of DNN and their results. DNN1 and DNN2 adopt original data sample as a training data set, while others implement random perturbation for data augmentation. Comparing DNN4 with DNN3, the training sample size increased. DNN5 added the training sample with low heat release rate comparing with DNN3. Our research is about training DNN with 5 different groups of data and simulating one-dimensional detonation tube, and then comparing the results of DNN with CVOD and theoretical values. DN1 uses original data sample as training data, and this picture shows the distribution of training sample. Though DNN prediction for typical major and minor species mass fractions agrees well with target values, DN1 does not perform well in the numeric simulation of detonation tube, and the detonation wave is decoupled. In the original dataset, data samples obtained from the low heat release rate region after the detonation wave have a large proportion. Including a large number of these samples in the training dataset may affect the predictive performance of deep neural network for the reaction near the wavefront. Therefore, DNN2 only used the original sampling data with a high heat release rate as the training data. The distribution of training data of DNN2 is presented in this figure. However, the detonation wave is also decoupled. The training data for DNN3 and DNN4 is generated by applying random perturbations with the same magnitude to all sampling data and constraining them based on the same heat release rate criterion. The effective perturbed dataset contains very few samples with low heat release rate. And once again, the difference between DNN3 and DNN4 is the size of training sample. However, different magnitudes of random perturbations are implemented to the sampling data with low and high heat release rates separately. To obtain the training sample set of DNN5. The training set of DNN5 provides good coverage of the original sample data in both the low and high heat release rate regions. All these three DNN have good performance in predicting species mass fraction. This picture shows the comparing results of different DNN and CVODE. It can be known that the DNN results agree well with CVODE. Without consideration of training data with low heat release rate, DNN results are slightly different from CVOD. After the detonation wave, the mass fraction of water is slightly lower, while the mass fraction of OH free radical is a little bit higher, comparing with CVOD results. Detonation cell size and other parameters are highly sensitive to the chemical reaction process, and the OH free radical is a key parameter that characterizes the hydrogen and air chemical reaction process. Therefore, accurate simulation of OH mass fraction is crucial. Moreover, the results of DNN3 and DNN4 show that enlarged training dataset has little influence on DNN predictions if the size of training sample is already proper. According to experimental and numerical simulations, the peak pressure of detonation wave oscillates slightly, even in the relatively stable propagation stage. Applying DNN in the simulation can also capture this feature. This table lists the CJ parameters of DNN calculation and the relative error. DNN3 and DNN4 give accurate CJ state parameters with small error, and the relative error of DNN5 is a little bit larger. Considering low heat release rate training data actually affects the prediction of deep neural network in the chemical reaction region near the wavefront. Therefore, training data with low heat release rate is dispensable for DNN predicting CJ parameters of detonation wave. If DNN calculation is performed on GPU, while CVOD simulation is performed on CPU, the speed-up ratio of DNN is 17.05. The conclusion of our research are as following. First, applying random perturbation is an effective data augmentation method. When disturbed data covers original sample well and the amount of disturbed data is sufficient, increasing training sample size has little influence on predicting effect of DNN. Training set should be mainly based on the data with high heat release rate and a large gradient near the detonating front, where the data with low heat release rate is dispensable for DNN prediction. And the speed-up ratio of DNN is 17.05. That's all. Thanks for your listening.
Okay, thank you for your presentation. Any questions? Okay, I'll have a. So for your training database, because detonation is a high pressure combustion, so what is the typical temperature and pressure ranges of your training data for this simulation? I mean, when you prepare the database for training, what is the considered temperature range and pressure range, initial pressure and initial temperature?
Okay. And this is the sample data. This is the sample data, original data.
Okay.
And the data can be divided into high heat release rate and low heat release rate. The lines is about at here.
Okay.
Mm.
So, okay, so go ahead.
if we implement random perturbation, and we can get the data. We can get the training data only including high release rate data, and this DNN model has a good prediction effect.
Okay, so for low heat release rate ranges, you use the CVOD directly.
Yeah.
So it's
No.
or you still use the neural network.
Still use the model because it's far away from the detonation wave, and the results didn't affect the calculation around the wavefront. And the result behind the wavefront is it has a little difference.
Okay, but generally the predictions are better with high release rate ranges. Am I right about this?
Yeah, the CJ parameters can be predicted more accurate.
Okay, okay,
without the low heat release rate disturbation.
Okay, okay, thank you. So any more questions? Okay, no. So thank you for your presentation again, and let's close this session.